Good afternoon. The topic for today is Gauss's law. Gauss's law is useful for calculating electric fields of highly symmetric charge distributions. The way we're going to start to talk about Gauss's law is to talk about a concept called electric flux. Electric flux is a measure of the number of electric field lines that penetrate some surface. If the surface being penetrated encloses some net charge, Gauss's law says that the number of lines that penetrate the surface would be proportional to the net charge. We'll develop this quantitatively in a short while. And to boot, this is independent of the shape of the surface. Let's take a really simple example first. Suppose I have a uniform rectangular surface and I have a uniform electric field that is, even though it doesn't look it this way, suppose it's perpendicular to the flat surface. If that's the case, we would say that the electric flux would be equal to the magnitude of the electric field times the area of the surface. In this case, it would just be the area of the rectangle or the square or whatever it is. On the other hand, if it was at some angle, if it wasn't directly perpendicular to the surface, there would be a factor of cosine theta, where theta would be the angle between the field lines, let's say, and the surface. So that would be my angle theta. So it would be decreased by a factor of cosine theta, since cosine theta can't be greater than 1. On the other hand, we can take it to extremes. If the field lines are coming parallel to the surface, such that theta is 90 degrees, of course the flux would be equal to 0 in this case. Now there's a better way to quantify this, and we'll see this as we go along. Suppose I have some arbitrary looking geometry. What I'm going to do is divide the surface up into little elements of charge. And I'm going to say if I have a field that's penetrating the surface, I'm going to look at particular area elements in the surface, and I'm going to say the following. Any particular element will have some little amount of flux, I'll call it delta phi, equal to E, the lines that penetrate that surface, dot delta A. In this case, what do I mean by an area vector? Very important concept. An area vector is that vector that's perpendicular to the surface in question. So if I'm looking at, let's say I'm looking at a surface, just a rectangle, that lies in the YZ plane, let's say, just for example, or in the XY plane. The area vector would be the vector that's perpendicular to that plane, or it would be in the Z direction. So even though it sounds peculiar to talk about area, which we know is a two-dimensional idea, even though it sounds peculiar to talk about a vector, the vector that's associated with that area is always perpendicular to that area. That being the case, I can break this surface up into even smaller and smaller charge elements such that I can take the limit as delta A goes to 0 of E dot delta A. And of course, if I sum up, if I want to know all the total flux for that body, what I would do is to sum up all of the fluxes of each charge element of the body. Then I'm going to take the limit as delta A approaches 0 which turns my summation into an integral. So I can write my integral as E dot dA. And what that says is the electric flux attributable to lines of E passing through that surface is going to be equal to the value of E dot dA. Usually we're dealing with flux lines through a closed surface. Now, this calculation would be very painful unless we have nice symmetrical geometries to deal with. Let's do a really simple case. Now, I'm going to state right off that the answer is already known before we even do the problem. We'll just show that we get the right answer. Let's suppose I have a cube and I have an electric field, uniform electric field oriented in the x direction of this cube. Let's say the cube has a side L. And I want to find what the net flux is for the cube. Now we said that the net flux is equal to the number of field lines that go in and go out. In this case, since it's a cube, I have as many field lines going into this left face as I do coming out of the right face. So immediately I can say, well, the flux, the net flux for this surface is going to be 0. And that's correct. But let's show by way of working this out why it has to work that way. First of all, take advantage of the fact that the electric flux is the integral of E dot dA. Let's look at the 4 surfaces that are parallel to the lines of E. Those would be the top, the bottom, the back side, and the front side. Each of those surfaces is parallel to E. So the flux in each of those cases is identically 0 because the angle between E and dA is 90 degrees. E dot dA would be 0. For the 2 faces that are perpendicular, however, let's look at the far face. The area vector is pointing in the same direction that the electric field is pointing, so E dot dA becomes equal to E times the area, which is L squared. So this is for the right face. For the left face, we can say that E is moving left to right, but the area vector for the left face is right to left. Therefore, the angle between E and dA is going to be 180 degrees. The cosine of 180 degrees is -1. Therefore, the flux for the right face, for the left face, is going to be minus EL squared. So when I add the 2 fluxes, I get 0 for the left face and right face. I have 0 for the other surfaces. So the total flux for this is 0. Now, that's a trivial problem, but at least it illustrates how we use the area vector to compute electric fluxes. There are some cute examples that you can do for electric flux. For example, I love to give this one because it scares people. I say, suppose I have a cone, and I have an electric field call it E naught. That's impinging upon the cone from the left. And I say, find the electric flux for the cone. At least for the lines going. Now we say, of course, there's no charge, the lines going in equal to the lines going out at 0. However, the question is, what is the flux for the lines coming in through this face of the cone? And of course, people immediately begin to worry. They begin to say, I should have paid attention in high school that day when we talked about the area of cones. I don't remember the area of a cone. Well, it turns out that for these kind of tricky problems, you don't really need the area of a cone. All you have to do is look at what is the largest area that those field lines can impinge upon. And if you look at the cone carefully, what you'll see is that you really have a triangle. It's really just a triangle that the cone is going. So if I have let's say I have a radius of r and a height of h, the area of that triangle is just going to be 1/2 the base times the height, or 1/2 r times h. And so in fact, they'd use the whole base, so it would be 1/2 2r times h, or just r times h. And therefore the flux would be simply E0 times r times h. So there are some tricky problems you can ask. You just have to be very careful to look at the picture and assess the geometry correctly. Generally speaking, it's a much easier problem than you think on the face of it. Well, that's all very nice, but what we really want to do today is take advantage of Gauss's law to help us calculate electric fields. That's where the beauty of Gauss's law lies. As I say, you've got to have high symmetry. It's not to say Gauss's law doesn't work. Gauss's law is always true. In fact, it's one of the 4 fundamental equations in electromagnetic theory, one of the 4 Maxwell equations. It always works. The problem is that unless you have high symmetry, the calculations are unbearable to do. So, we can say that, let's do this. Let's consider a point charge. And let's give it some value, little q. Let's say it's at the center of a sphere. And let's call the radius of that sphere capital R. Now, we know the answer already. We don't have to use Gauss's law to do this. We know from Coulomb's law that the value of the electric field at any point on that surface, E, can be written as Q over 4 pi epsilon naught R squared. And of course, the field points radially outward. So if I were looking at this point on the surface, the E field would point in that direction, and so on and so forth. So we already know the answer. But we're going to use this and take advantage of this to develop Gauss's law. So I know that E field lines point radially outward. I also know that an area vector at this point points in the exact same direction as the E field lines do. So E and what we might call delta A are parallel to one another, which is to say that the normal component of E and delta A just equal to E times delta A. And the flux then, we can very simply write, the electric flux is just going to be E times the area. Now, of course, the area for the sphere is 4 pi r squared, so I can write this as E times 4 pi r squared. So I can say, moreover, I know the value of E from Coulomb's law. Coulomb's law is Q over 4 pi epsilon naught r squared. So I can write then the flux as Q over epsilon naught. This is Gauss's law. My electric flux is equal to, I'm going to be a little more specific here, I'm going to write Q as the enclosed charge. Whatever charge is enclosed by the surface of interest divided by a constant epsilon naught. Now you can probably guess why Rather than using the constant K for Coulomb's law, we use 1 over 4 pi epsilon naught. It makes the 4 pi's disappear. Very convenient for us. Well, the sphere is really nice, and you might say, does that matter? Does it have to be a sphere? And the answer is no. It doesn't matter what the surface looks like. I'll get the same answer for the electric flux. Gauss's law is the same. It just depends upon, the flux just depends upon the amount of charge that's enclosed by the surface. So it's very convenient. On the other hand, suppose I have some blob surface and I have some point charge outside the surface. Notice, in this case, the surface isn't enclosing any charge at all. And therefore, because there's no enclosed charge, the flux is 0. The only thing that counts is when you enclose the charge. That's extremely important as we go deeper into Gauss's law and calculating electric fields. Suppose we had many, many point charges, or some continuous distribution of charge. That's even better. We can use the superposition to say, right off, I just incorporate all of the charges, however many charges there are, to make however many fields. And I'm going to get the same thing. It's going to give me my electric flux is equal to that integral, E dot dA, and that will just, again, be equal to however many charges are enclosed over epsilon naught. You can do it for a series of point charges. Of course, it's much more interesting to do for a body of continuous charge, such as a cylinder or a sphere. We'll do that as well. So without any further ado, let's use Gauss's law and do some applications. We'll show some nice examples. We've already done the E field due to a point charge. So we can use that if we want to work in reverse. Suppose I say, what is the electric field at some point r, some point, a distance r away from a point charge? This is how I would use Gauss's law to find the electric field. Yes, we already know the answer, but this is a very powerful technique. What I want to do is the following. When I'm at this point, I'm going to say, what is a very symmetrical surface I can draw whereby the electric field, due to whatever charge distribution I have, is going to be constant along that surface? In the case of a point charge, the simplest drawing to make is a Gaussian surface. We call this a Gaussian surface that has a radius of r, that in this case is a Gaussian sphere, a radius of r and an area of 4 pi little r squared. And we apply Gauss's law. We say that the integral of E dot dA is equal to the charge enclosed divided by epsilon naught. The beauty of this method is the following. All along, at every point on this Gaussian surface, E is constant. It is also parallel to dA at every point. So dA at this point is pointing in the same direction that the electric field would be. They're both along that radial direction from this point charge on outwards. So that turns my integral simpler in two ways. One, because E is a constant, I can pull it outside of the integral. And because E dot dA is E and dA point in the same direction, I can very simply write E times the integral of dA is equal to Q enclosed divided by epsilon naught. And of course, now I'm only having to integrate dA. Well, for a sphere, dA is just 4 pi r squared. So that's, and the charge that's enclosed is just this point charge Q. So I divide by epsilon naught. And then, of course, my electric field is simply, as we expect, Q over 4 pi epsilon naught r squared. That's the simplest example of how to use Gauss's law. We'll do a number of others that are a little bit more fun. Suppose I have a spherically symmetric charge distribution. So this whole sphere got a spherical distribution of charge, and let's say that the total charge of the sphere is Q. Let's say that the radius of the sphere is capital R. And we say to ourselves, I'd like to find the electric field at some point outside the sphere. Let's do that first. At some distance, we'll call that little r. So what is E outside the sphere of charge? Now, the assumption is that the charge is uniformly distributed throughout the sphere, what we would call an insulating sphere. We can do a non-uniform distribution, but we'll save that for later. So what I'm going to do at this point is to say, if I want to find the electric field at this point down here, call it point P, I would draw a Gaussian sphere that has a radius of little r, and I'm going to apply Gauss's law. Once again, because of the spherical symmetry, I know that at that point, the electric field is going to be in the same direction as the area element. So integral of E dot dA immediately becomes, and E will be constant anywhere along that surface. So I can pull E out of the integral. E and dA are in the same direction, and that's going to be equal to how much charge am I enclosing? Well, I'm enclosing all of the charge of that sphere, Q, over epsilon naught by Gauss's law. dA for a sphere is going to be 4 pi little r squared is equal to Q over epsilon naught. So the electric field outside the sphere would just be Q, the total charge of the sphere, divided by 4 pi epsilon naught r squared. Sorry, little r squared. Amazing, huh? So whether I have a point charge or whether I have a sphere of uniform charge, outside the sphere it looks the same. It looks as though all of the charge had been located right at the center of the sphere. It looks like another point charge. It's kind of interesting how that works. Let's make it a little bit more interesting though, and let's ask, what about the electric field inside the sphere? So suppose I want to find the electric field at some point P that's some distance little r, which is less than big R away. Gauss's law still applies, so integral of E dot dA is still the charge that's enclosed divided by epsilon naught. But in this case, I'm not enclosing all of the charge when I draw my Gaussian sphere. I'm only enclosing some of it. The question is, how much charge am I enclosing? Well, that's where the key word uniform comes in. If the charge is uniformly distributed throughout the sphere, I can say that the charge enclosed divided by the volume of my Gaussian sphere, 4/3 pi r cubed, has to be equal to the total charge of the sphere divided by its volume, the total charge of the given sphere. And so I can very simply compute the charge enclosed. 4/3 pi's go away, and I get that charge enclosed is equal to Q little r cubed over big R cubed. Gauss's law tells me that, yes, again, the electric field at this point and the area vector are perpendicular. The field is constant at every point on this Gaussian surface. Therefore, I can say E times 4 pi little r squared is equal to charge enclosed Q r little r cubed, big R cubed, epsilon naught. And so my electric field then is just going to be Q r over 4 pi epsilon naught capital R cubed. So that's how you would calculate the electric field for inside a uniformly charged, what we would call an insulating sphere. Do another example along the same lines. It's going to sound repetitive, but we'll move to other geometries in a moment. Suppose I have a spherical shell. And suppose I have it's a uniformly charged shell. And I say, what is the electric field inside the shell, that is somewhere in here? So suppose this is the center. Suppose I want to find the field at this point. What I can do, draw a Gaussian surface, and immediately you see this is not enclosing any charge whatsoever. So the electric field inside the shell is 0. On the other hand, suppose the total charge of the shell again is plus Q. If I want to find the electric field outside the shell, maybe some distance r from the center, once again I draw a Gaussian sphere. Once again, the electric field is going to be constant everywhere on the sphere. The area vector is parallel to the electric field at that point. So I can say that E times 4 pi little r squared is equal to the charge enclosed. In this case, it's Q divided by epsilon naught. So E is equal to Q over 4 pi epsilon naught r squared. Once again, it's as though all of the charge in this shell was located at the center of the sphere. That's the amazing thing about Gauss's law.